area between curves. When you see area, perhaps you have an inclination that integration is going to be involved, and you would be correct. So let us review the geometric interpretation of the integral. We're just going to work with a singular function in the coordinate plane. So let me introduce some function f. If we're integrating from this point A to this x-intercept b, we know that the integral represents this region of space that is between the function curve and the x-axis along that interval a to b. So this would be and we're going to integrate with respect to x, and that area measure is positive. And we'll talk about why in a second, or we'll at least review why. Then if we were to integrate from b to the next x-intercept, this point C, that region of space is represented by the integral from b to c, and it is an area calculation, once again, between that function curve and the x-axis. So integrating from b to c of f of x dx will get us this area. However, this area is going to output a negative value. So as a review, if we were to integrate from a all the way to c of f of x dx, or really along any interval, but using this example, we should realize or remember that this represents a net area along that interval, okay? Because what's above will be interpreted as positive and what's below will be interpreted as negative as long as we're integrating from a to c where a is less than c. So why is it positive and why is it negative in those respective locations? So as a review, the integral is calculated by taking the area of a rectangle in that region of space, and we're going to introduce many rectangles along that region, and we're going to sum those areas. And when we take the limit as the number of rectangles in that region approaches infinity, that will produce the integral along that interval. Now, what does the integral contain? Well, we have an integrand, which is some function. Now, that function I like to think of as the height of our rectangles. So if we're just working with a singular function there, think of it as that represents the height of your rectangle, and the reason why we'll look at again geometrically in a second. But also we have this dx portion, that differential is going to represent the width of your rectangle. And that's really that change in your input, that change in x. And that gets you the width or the base. So we're summing areas of rectangles, and as the number of rectangles in that region of space approaches infinity, we get an exact representation for the area between the curve and the x-axis. So let's look at these regions of space a little more closely as to why the area will be interpreted as positive or negative depending on whether we're above or below. So under the assumption that we're integrating from, say, a to b, where a is less than b, that means the width of our subintervals that represent each base of the rectangle is always going to be a positive measure. Therefore, if the height is represented by the function output at some point along that interval, you'll see that when it's above the x-axis, the function output is greater than 0. It's positive. And if the width of our rectangle is greater than 0, well, then we're going to have positive areas for each rectangle. So in sum total, over a region of space where the function is above the x-axis, that area will be positive. If we look at the region of space where we're below the x-axis, using that same thought process, your change in input, which represents the width, is still going to be positive as long as we're working from b to c where b is less than c. The function output is now less than 0. Therefore, the overall area for each individual rectangle will be interpreted as negative. So in sum total, that area below the x-axis will be negative. Okay? So that is, again, a quick review of why area above is positive and area below is negative, as long as we're integrating along an interval where the first point of the interval is less than the second point. Okay, if you were to reverse the direction of integration, so say we went from B to A, where B is greater than A, well then your width is now interpreted as a negative value, so what's above the x-axis will turn to negative, and what's below will turn to positive. So the direction of your integration actually matters, right? Because that dictates the base. So as long as we're integrating from least to greatest in terms of the interval values, you'll get a positive width, and then you can always remember that what's above is positive and what's below is negative, and if you change direction, that thing switches. So now that we've done a quick review of the geometric interpretation of the integral, let's talk about area between curves. So we're going to look at three scenarios. Our first scenario, let's assume both function curves are above the x-axis for the region of space we're trying to calculate the area for. So we have f and g, and we're trying to calculate this region R in here. So area enclosed between the two curves. Scenario 2. Let's say that one function is above and one function is below. And then scenario 3, let's say they're both below. Now you notice that there's no enclosed area in the second scenario, so let's mark off our limits of integration on both cases. So we're going to integrate from this point A to this point B, which happen to represent the intersection points of f and g. Now there's no intersection for f and g, so we're just going to look at some arbitrary values for a and b, and we'll look at the region of space that's between those two curves along A to B. And then for the third scenario, we'll look at this point A and this point B, and we're going to look at that enclosed region R. So first scenario, if we wanted to calculate that area of that region R, what we just reviewed is that integrating from A to B would represent the area between the function curve and the x-axis. So if I integrate just f, I'm going to get this enclosed space, which I'm going to outline now in blue. We can see if we can remove the area that's below that g curve, we'll be able to be left over with just that R region. So how do we get that region of space that's below the function g? Well, that's also interpreted as the integral from A to B of g, right? So the integral gives us, so I shouldn't do it in red, I'll do it in green. So what I have outlined in green is going to be calculated through integrating g from A to B. And again, as a reminder, to sound like a broken record, integration, area between the function curve and the x-axis. So what can we conclude? If I want to calculate that region R, so let's say the area of that region R is going to be equal to, if I do the integral from A to B of f of x dx, and then I subtract from it the integral from A to B of g of x dx, that'll get me the region of space that I want, that is enclosed between those two function curves. And we know from our integral properties that I could put these together because the limits of integration are the same on both integrals. So I could say we're going from A to B of f of x minus g of x dx. So let's jump over to the second scenario. I want to get this enclosed region that I'm going to outline in green, let's say. Actually, you know what? I'll stay consistent with colors. So let's do it in purple, what I'm looking for. And we'll reduce that thickness of that line. So let's say what I want is this space here. So still area between these two curves. So how can I find that? Well, if I integrate from A to B of the function f, I'm going to get what's enclosed in blue. And then if I integrate from a to b for the function g, I'm going to get what's enclosed in green. So it looks like if I want the area of that region that was enclosed originally in purple, I would take that blue region and add it to that green region. And one thing that should be mentioned that needs to be clear, this is a unit on the applications of the integral. So our goal is to utilize integration to answer, in this case, a geometry problem. So we're just trying to find the positive area of these regions in space. So we don't want the area to be interpreted as a negative value. So how do we get a positive area measure for this irregular figure? Through the use of integration. So that's important to recognize that we're using integration as a tool for an application to a geometry problem. We have these irregular geometric shapes that don't have just some familiar area formula to them, but we know the integral will calculate a net area over some interval. But we have to make sure we keep in mind that, again, we're trying to answer a geometry problem here. So this is an applications unit. So the question is, how do I make sure that that purple region in this second scenario is in fact interpreted as a total positive area for that irregular figure? And the reason I bring that up is because at the beginning of the video, when we reviewed what the integral tells us, we know that this area in blue is going to be positive, but that area in green is going to be negative. So how do we get that blue plus the green to be a total positive? Well, knowing that that area is going to be negative, if we still subtract a negative, we'll get a positive value in total. So what we're going to do here to calculate that area of space, we're going to integrate from a to b of f of x dx, and then knowing that the integral for g is a negative value, and knowing just from a geometric point of view that I want to add these two things together, I actually don't want to do a plus. Because if I do a plus, we're adding its negative value, and it's not going to be a total sum of this geometry problem where I want a big area. So it would actually reduce the overall area to just some small region. So we're going to subtract still the integral from g of x dx from a to b, because knowing that g of x is going to output a negative integral value, minus a negative equals a positive, so I'm going to get that positive total. And again, we can combine these. And let's move on to the third scenario. Region of space enclosed. We know integrating from a to b for the function f is going to get me this blue region. What I'm outlining in green is going to be the result of integrating g. So you may think that we have to do g minus f to get that region of space, but recall that these are negative area values when we integrate. So in fact, we're still going to reverse that thing to the point where it looks like we're going to take the area of region R is going to be found by doing the integral from a to b. We're going to do f of x dx minus, again, that might not make sense initially, but we'll talk about why. When we look at g, you think that if I do g and then remove f, I'll get what's left with r. But knowing that we need a positive area measure, because again, we're answering just a geometry problem, we're using integrals for an application purpose. If we have a smaller negative value in f and we subtract a bigger negative value in g, that's going to result in a positive value, right? Because the area for f is less than the area for g. So by subtracting the bigger one, negating a negative means a positive, and the overall value will be in fact positive. So we're still going to do f minus g. 'g" in this case. So one more time why that is. The area for f is a smaller negative value when compared to g. So knowing that I need a positive area total, I'm going to subtract the bigger one because it's going to negate that larger negative value to the point where it's adding a value that's larger than that f of x integral value, and therefore the overall area will be positive, which is what we're looking for. Now, f and g were conveniently chosen and located in specific points for each of these scenarios, but I could have swapped which one was f or g, but I did this specifically to show you that given f and g are in the same positions for every single one in relation to the other for that enclosed region, we can make a conclusion for any area between curves scenario as to how to calculate that using an integral, because what ultimately resulted in all three scenarios was the same integral. You'll notice that all three of these are exactly the same. But again, we have to be careful because I specifically chose f and x to be positioned in certain locations. So we want to make a generalization here on how to calculate the area between two curves so that we get that positive area value. So here's what we do. In all three scenarios, in the enclosed region in which we were trying to calculate the area for, you'll notice the f function was always above the g function. And that is the key. So we always do top minus bottom. This will equal the area between curves. Okay? This is the general approach that you need to take. And we should make a note that when we're integrating top minus bottom for that interval a to b, we have to make sure that a is less than b, right? So we want to integrate in the correct direction to utilize this general formula for area between curves. So that's really all there is to it. You just integrate from a to b, the top function minus the bottom function, and we saw the three different scenarios that could occur. But now let's make some additional considerations that you may need to implement when solving a problem that asks you to do this. Now that we know the general approach, we're going to area, we'll just write it again, a to b, we're going to do top minus bottom, again where a is less than b. Now I'm not putting the differential dx dy on the end because we'll take that into consideration as one of these things that we'll write down, but in general we're always doing top minus bottom. So the first consideration is, what if we don't have the limits of integration? So what if we don't know what a and b are? They're not given to us explicitly. We can see the region of space in which we need to integrate using an aid of a calculator, but we don't know what a and b are. So if we're not explicitly given the limits of integration, how do we find them? Algebraically, what we can do is we know the intersections of function curves can be found by identifying when these function curves equal each other. So we're going to set function curves equal to each other and solve. And there are your limits of integration. Consideration number 2. So let's say we've just given two functions, but we don't have a graphing tool to aid us in looking at a picture. We could draw one ourselves, but let's say, again, we're just given two functions, no picture, and we don't know which one's on top or which one's on bottom. How are we going to figure that out? Well, once we know the limits of integration, so that's important, we need to already find that first, whether it's given or we find it algebraically. To identify which function is on top, because as we know that's important for the general approach to finding this or answering these questions, we're going to evaluate the functions at a point within the limits of integration. So this is important. if you choose a point outside the limits of integration, you're picking a point that's outside the enclosed area, in which case you don't care about, because we're trying to find the area between the two function curves in this enclosed region. So you need to pick a point within the limits of integration. So you evaluate the functions, we'll say functions, at some point within the limits of integration. Then, here's the thing you're looking for. The greater output equals the top function. So whatever one outputs a greater value at that evaluation point is on top in that region of space. So again, the positions may flip outside the region of space that you're trying to calculate the area for, but you don't care because we're just looking at this specific region. So if we put a picture to this, kind of going back to our original picture, let's say we want this region R. We need to identify what A and B are, and you need to pick a point between A and B to figure out which one's on top. So if you pick some point C here, you'll see that what should happen is that F will have a greater output at C. So we'll see that F of C should be greater than G of C at that chosen value, which would indicate that F is on top. Again, so we should theoretically be able to do that without actually looking at a picture. So what we don't want to do is choose some C value outside that range of A to B. So you can't just pick whatever you want within the domain of the functions, because now you're going to see that the G output is in fact greater than F, and you're going to misidentify which one's on top for a region of space that you don't care about. So once we have the limits of our integration, once we identify which one's on top or which one's on bottom, the next thing we would want to do is make sure there's not a switch in position within our region of space. So this is best done visually. So let's say they want you to find the area enclosed from A to B between the functions f and g. So you can see that there's two distinct regions that we would have to sum together. We'll call this region R and this region S. So if the question asks, we want to work from A to B and find the total area enclosed between f and g along that interval, the thing is, f and g swap their top-bottom position along that interval. So how are we going to figure this out? Well, we're going to have to figure out where that position changes, which is at this point C, that point of intersection. We discussed before how we can find points of intersection. When you set the functions equal to each other, if you had to do this algebraically, you're going to get these points of intersection as well. So just make sure you identify that that point C is the value between that point A and B, which you should be able to recognize. Then we're going to just split this problem into two separate integrals. So if there's a switch in top-bottom position, just recognize we're going to have to use two integrals here. We're going to work from A to C, which we're going to have to find. The top function for that R region is G, so we're going to have to do top minus bottom. And then we're going to have to add on another integral that goes from C to B, where this time we're going to do f minus g because, again, the positions of these functions have switched, where g was the top in the first region from A to C, and then f became the top function from C to B. So if there's a switch in position, all you have to do is split up this problem into multiple integrals. So there could be more than one change in position, but we know the general approach to finding the area between two curves is integrating the top function minus the bottom function always. So once we've just identified top and bottom, you can work from there. Then the last consideration is integrating with respect to y. Now, why would we want to do this? Well, sometimes the region of space in which we want to calculate the area for is a simplified problem when integrating with respect to y as opposed to x. And here's a region of space that's contained between this curve function f, this linear function g, and the x-axis. If we were to find the area of this region, integrating with respect to x, we would have to do the following. We would identify this point A. We would have to identify this intersection point C, and also this x-intercept with g, which we'll call B. And we would have to split this region into two separate integrals, because the function g is not involved in the interval from a to b. So what we're going to do is we're going to say the total area for r when integrating with respect to x would be calculated by integrating from a to b of just the function f. And the reason why we're just doing f is because when we started this video, again, integrating f is going to get us the area between the curve and the x-axis, which will be this region of space, which I'm now outlining in purple. So you'll see that g is not involved whatsoever. But then we add on this region of space, which is the area enclosed between two curves, f and g. So then we're going to have to integrate from b to c, top function minus bottom function. So two integrals are needed to calculate that total area for r. But what if we change our perspective so that we integrate with respect to y instead? If we're going to do that, the first thing you always need to make sure is the case. If you're going to integrate with respect to y, is make sure your functions are redefined in terms of y. So if we have f of x and g of x, meaning we have y equals some function of x given to us, make sure you take those functions and you solve for x so that they are now functions of y. So we're going to have to make g of x and f of x into functions of y. That's always going to be your first step. So that's the first thing you're going to have to take care of. Now, why would you want to integrate with respect to y instead? Well, here, that intersection point, which we'll introduce as a point D, if we integrate still from least to greatest along the y-axis, so we're going to go from a to d. If we change our perspective a little bit, we're going to see that this function g is on top of the function f with respect to the y-axis. And that region of space can be found by just integrating a to d of top minus bottom. But again, make sure your functions are defined in terms of y now. So we're going to do top minus bottom. And top minus bottom, I'm talking about in relation to the y-axis now in dy. So this same problem can be solved by computing one integral if I change my perspective as opposed to breaking it into two integrals. Now, let's just make a note. So if we're going to integrate with respect to y, the top is equal to the right function, and the bottom is going to be equal to the left function. And the reason for that is that the positive x-axis indicates the positive output location for functions defined in terms of y. So something would be on top if it's to the right, and the negative axis for x obviously runs left, so the bottom would be left. So the outputs for functions defined in terms of y, positive goes right, negative would go left, which is why top and bottom are structured as follows. Okay? So changing your perspective, integrating with respect to y is equally valid as integrating with respect to x, and you should get the same exact answer with either method, because the area of that region of space has not changed. You're just changing your perspective. So the area calculation should be the same with whatever method you choose to do, but the key is here. Make sure you're reformatting your functions. So don't integrate the same functions as before and just change the x variables to y variables. You actually have to manipulate the formula so that you have x equals some function of y in each case. So those are all the considerations that need to be made, and that is how you integrate multiple functions to calculate the areas between function curves.